Andrew was so kind to already point out the main components of an MR system, which is the main magnetic field, of course, the gradients. And as you heard before, and the RF coils. And as you heard before, you have to come back next year and the year after to get them all. So today will be on RF coils. And those come in many different sizes and shapes and looks and geometries. And the aim of this talk, or of this educational, is to give you an insight why that is, first of all, and how you can do it, and hopefully give you an aid in choosing the right coil for your application and your experiment. To begin with, we have to clarify two things. First of all, coil. In the physics world, a coil is nothing else than a wound wire represented by an inductance L. In the world of MR, a coil is a resonance circuit. So when MR people talk of coils, they always mean a resonance circuit, which includes a capacitance as well, and which leads to a resonance frequency of the whole circuit. This resonance frequency is, of course, dependent on the capacitance and on the capacity and on the inductance, and, which is most important, if this resonance frequency is equal to the Larmor frequency, then you can, via the resonance effect, excite and manipulate the atomic nuclei in an atom. And this is actually quite amazing, I think, because this very, very weak radio frequency energy you put in is able to manipulate atomic nuclei where the forces are very strong. And this only works via resonance. In addition to the capacitance, you need to match the coil, as it is said, which basically means you adjust or match the inner resistance of the coil to that of your preamplifier and of your reception pathway. And of course, in every real physical or electrical system, you have a resistance which takes away parts of your energy and which leads to losses. The second point is transmission and reception. As Andrew already pointed out, you can use those coils for exciting your spins as well as receiving the signal they generate. You can excite them only if your coil is tuned to the Larmor frequency. If you have that, then you generate with your coil a magnetic field called B1, corresponding to B0 being the main magnetic field. And the B1, if this is perpendicular, that's important, has to be perpendicular to the main magnetic field. It is able to excite the spins and flip them, or the spin ensembles, and to flip them into the XY plane so that your coil can receive it. This takes place at very reasonable powers, being in the range of watts to kilowatts. And this rotating magnetization within the XY plane then introduces an electromotive force within the coil. And the voltage induced is proportional to the main magnetic field, as we heard before, proportional to the B1 field you applied, and of course proportional to the netto magnetization you have before exciting, so the spin ensemble netto magnetization. A big difference is, of course, the power received. This is in the range of microwatts to milliwatts. That means your coil, if you have a coil which does both, your coil has to be able to transmit quite comparably high powers and receive comparably low ones. But it is possible. But taking into account the Reciprocity theorem, which says the sensitivity of a magnetic resonance assembly used as a receiver to nuclei present at a point A is proportional to that assembly's efficiency when used as a transmitter to generate at the same location A a radio frequency field B1. This basically means what's good for transmission is good for reception. The homogeneity you have while transmitting in a certain point is equal or proportional to the sensitivity you have when receiving. This means, on the other hand, that nearly everything I'm going to talk about in the following is valid for both, for transmit coils as well as for receive coils. So I will not, in general, not make a big difference there. So what do we need for an RF coil? An RF coil has to have in ascending importances. I've listed those. It should do a low distortion of the original field. Of course, if you bring something into a main magnetic field, you distort it. This is mainly important for small coils. For large coils, the effect isn't that big. You need a mechanical stability, because many coils, especially in biomedical applications, you put in and take out again, so they should be halfway mechanically stable. You need, and this is not to be underestimated, a comfortable access to the sample. This is not that important in NMR spectrometers, where you just want to do a spectrum and it stays in a long time anyway, and you don't need to monitor any life signs as breathing, and you don't need any access for anesthesia or some other things. Different in human applications and in biomedical applications, where you need to put in and out the mice or the patients, and you need to monitor their life, their breathing and their heart rate, for example. You need an homogeneous B1 field, because you want to excite the area you want to see as homogeneous as possible, so that you have the flip angles the same everywhere. And this is of utmost importance here, you need a high signal-to-noise ratio. That's why we go into the signal-to-noise ratio again, even though you heard about it before. The signal is rather easy. I already mentioned it. The induced voltage in the coil is proportional to the B0 field, to the excitation field, and to the net magnetization. But the noise gets more complicated. The noise induced in the coil, so the noise voltage induced into the coil, is dependent on the temperature, some other tissue-related factors, and the resistance of the whole system. The resistance, meaning losses, is equal, in that case, mostly equal to the noise. Okay, so let's have a look at the resistance. The resistance, or the losses, divide into the coil losses related to the coil and to the whole electronic setup and to the object. If we look at the coil first, of course, as Andrew already mentioned, the Brownian motion, this Johnson noise or resistance, is simply due to the temperature and to the movement of molecules and atoms within. Then, in addition to that, you have a so-called skin effect. The skin effect means that if at high frequencies, the currents, the alternating currents, will tend to flow on the surface of the conductors. And this shortens the effective cross diameter of the wire where you have the currents flowing, and of course increases the resistance with that. And the skin depth is proportional to the square root of the Lama frequency. So the higher the frequency, the more the skin effect will affect you. And then if you have a coil, as a classical coil, as a classical solenoid coil wound, you can get into the trouble of a proximity effect. If those are too close, then the electromotive forces will start to interact. And if you haven't built your solenoid coil properly, this can increase the resistance and therefore the losses by up to 10 times. So it is very, very crucial that you have good geometries there. Coming to the object noise, the object losses and created noise by the object, there's two main things. There's a loss related to magnetic fields and a loss related to electric fields. The loss related to the magnetic fields originate from currents induced in conductive material of your sample. And this dissipates power, of course, and while receiving induces noise again. It is the dominant effect for high fields and large samples, and it heavily relies on the so-called factor B, or the filling factor, meaning how much of the sensitive volume of your coil sees the sample, right? So that would mean, okay, well, I just put the sample outside of the coil. Then you don't see anything anymore. So there's not much you can do about that. This problem remains and stays, because unless you can choose your sample and just take a non-conductive sample, but that is not the whole idea of it. So you cannot do much about it unless you only need to scan a part of your sample. I'll come to that later with surface coils, but for example, if you just want to see the spine and not the whole body, then you take coils which are close to the spine, along the spine, so you reduce the part of the sample which is seen by the coil. The electrical related resistances or losses are due to two reasons. First of all, dissipative displacement currents in dielectric media. If you have a dielectric media and you apply an electric field, it tends to move and to balance out the electric field. And this, of course, causes losses when transmitting and when receiving. And the far field. If you take it very wildly, an RF coil could be, or not could be, but is similar to a normal radio antenna, where you want to dissipate the energy far field. This you want to avoid in an RF coil. You want to concentrate all the energy you put into the volume, inner volume. So if you have far field radiation, then principle of reciprocity, then you can receive with it as well, and you don't want to receive your local radio station with it, so you try to tend to keep all electrical fields outside of the interesting volume, and you'll try to symmetricize your electric fields as good as possible. So those two are something, this one especially is something you can do something against. Okay, as I said, there is losses due to the coil and losses due to the sample. The ratio of those, or the influence, is of course dependent on the ratio. If you have a body coil or a human coil, then the sample losses dominate the noise you receive. And if you have microcoils where the sample is negligible compared to the lot of wires and cables and coil you have, then the coil losses dominate. Here you see the ratio, for example, for a microcoil is 1.2, and the ratio well, this in fact is actually a head coil, but even if someone is in, then it is around 4. Now, how to judge the quality of your coil? Of course, the ultimate experiment to test your coil is your experiment itself. But to get an idea, once you just have it on the bench, the quality factor is quite often used, which gives you the ratio of the energy stored in the circuit to the energy lost per cycle. This is rather easily measurable if you take a simple network analyzer and you sweep through the frequencies. At the resonance frequency, you will have an absorption. If you then take the half width of the absorption peak, or simply at the line width, you will get a measure for the quality of your coil. This measure should not be taken absolutely, at least the values are not absolutely. More reliable are relative contributions. Sorry, I'm always shooting into your direction. The relative contributions of the loss mechanism. So depending on what you load the coil with, the sample influence changes. Easy example, empty is clear, but if you put in distilled water, you have nothing which can conduct. So all losses you will see will be to electrical fields, as you have a dipole inside, right? Water are dipoles, so the losses you get are only due to electric field losses. Whereas if you put a saline solution in, then your sample can conduct, and you see the magnetic losses as well. Silicon oil should in that case be more or less equal. So if you have a look at those values for different loadings, then you can really tell the coil, okay, the coil does see a little electric field in this example and is quite sensitive to loading where magnetic interactions take place. Okay, now what should the coil look like? The ideal coil structure would be a sphere with currents running parallel to its equator, and these currents being sinusoidally modulated with 0 at the poles and maximum at the equator. This is just so of course analog, not digital, not on only a few places, but the whole sphere. Well, this has actually been built by David Holt once, but has a few drawbacks which are obvious. You have a spherically limited sample. It has to be spherical or fit into the sphere. You have very limited access to the sample at all. And that's why usually you have cylindrical geometries, as the magnetic bore is cylindrical as well. So this is the sinusoidally modulated current you would like to have. There are two different types of cylindrical coils. Ones which have longitudinal fields, being the B1 field parallel to the axis of the cylinder, and transversal. I will quickly go over those in the following few slides. If you have a cylinder, the ideal field, the ideal current distribution on the cylinder, if you want a longitudinal field, would of course be an equally distributed current running around the cylinder. If the cylinder is indefinitely long, then you get the perfect homogeneous B1 field inside of it. Best approximation to that is a solenoid. It comes very close, and if the length of the solenoid is large compared to its radius, you get nearly a perfect homogeneous B1 field inside. A big problem of that, the problems of those are two. First of all, geometry again, because if you place this cylinder on the cylinder axis of the solenoid parallel to the bore of your magnet, your B1 field will not be perpendicular or will be parallel to your B0 field. So the main magnetic field will be parallel to the excitation field, and so you can't excite anything. This means that you have to turn it 90 degrees, and then again you run into troubles having access to your sample. So this is limited access in biomedical applications. The other problem is self-resonance. If the length of the whole wire approaches the wavelength of your frequency, then you tend to get standing waves within the whole wire, and you're not able to excite a sample anymore because those cancel out over the field of view. Ways to get around that, especially around the self-frequency, is having parallel turns, as in the example C, or having a so-called loop gap generator, which just is one large sheet going over. The problem with that one is that it only works at really high frequencies because of its rather low inductance. To get around the geometry conflicts, you can have the following workarounds, which is a classical Helmholtz coil, which has lots of applications in physics everywhere, which is basically two turns or more turns on one spot, divided or separated by their radius. So this distance in between here and here is the radius of that turn. Doing that, you get a quite homogeneous excitation field, and you can access in between those two loops. A radical variation, but often used, of the solenoid is just having the turns in one plane and using the coil as a surface coil, placing the coil underneath or the sample on top of the coil. You can do that with multiple turns or just with one turn. These have two obvious problems. You have a very low homogeneity axial to the coil and a limited field of view parallel to the coil as well. to overcome this, surface coil arrays have been built. So just a lot of surface coils beside each other would be a petal resonator, or a switched array, which is the principle is still in use a lot, where you can turn on and off certain coils, adjust them to the field of view you want to see, and turn off the others you don't like, which only would generate noise. And a phased array coil, where every coil, which are decoupled geometrically, you can avoid or reduce the coupling between the coils if you overlap them. And they all have their own preamplifier and their own reception pathway. This allows to put narrow-banded filters in there, and increase the signal to noise there. The main advantage of those is that you increase the planar field of view. So parallel to the plane where the coils lie in, you're able to increase the field of view and adapt it to the sample you want to see. In addition, you're able to use, if you have separate reception pathways in phased array coils, you can use the information or the knowledge you have on the sensitive volume of each coil to reduce your scanning time, because you know this coil's signal had to come from that area, so you can reduce the scanning time factor 2 up to 4. One quick example for that, this is a picture of a red body acquired with a body coil. If you'd have 4 elements, those would be the areas of which the elements see. If you know that in advance, then you can do parallel imaging techniques to speed up your imaging. And the combined picture is clearly superior in SNR and yields good information at shorter measurement times. So those were the cylindrical probes with parallel B1 field. If you'd like to have a transversal field, then what you'd need is a current running around, basically, or on the outsides of the cylinder, and modulated sinusoidally with the angle. So you need zero currents up on top and down there, and maximum current densities at halfways. This is not that trivial to build as the other ones. The easiest approximation is just a single loop on both sides where you need maximum current density, and send it in and out again. Then you mimic the sinusoidally needed current distribution on 2 places, right? On the right and left side, and of course where it's zero. An improvement of that would, you can, of course, to reduce the complete cable length, again to prevent standing wave effects, you can break those on both ends by a capacitance. This has the other advantage as well, that it symmetrizes the electric fields within, and you reduce your electric losses. An improvement of that is having equally currents at 60 and 120 degrees. So in this case, you mimic the ideal current distribution at 6 positions, and again, you can split those with capacitance to symmetrize the electric field and shorten the total cable length. And you can do that, of course, in parallel or in series. Another smart design is the so-called Alderman-Grant coil, where you basically have sheets of conducting material on both sides. And historically, this was the first design to use end rings, where you have grounded rings at both ends to keep the electric fields out and optimize in that manner. An approximation of that is the filament coil type, where you have different spacings between the filaments. So at 0 and 180 degrees, you have large gaps between, which get closer, coming to the area of maximum desired current densities. And if you project those, then they would be equidistant. So that's the way you space them. You can drive that as far as you like. So the approximation is arbitrarily close. The more filaments you take, the closer you get. And now we come to the coil, or the most used coil, which is the birdcage coil. Its predecessor has a very smart idea where the cable length and the cable itself is wound around a toroid cylinder and has exactly the desired wavelength, so that within, it's now using the standing wave effect. Within, on the inner side of the cylinder, you produce exactly the desired sinusoidally modulated current density, and the outside elements work very well as shieldings. A similar idea was the birdcage resonator. And the birdcage resonator is, or at least I understood it, or is quite good understood, if you imagine a high-pass element, a high-pass filter element, which consists of a capacitance and an inductance. For symmetry reasons, I put in two capacitances. If you put in an alternating voltage, you'll get a voltage out with the same magnitude, but with a phase delay. And this phase delay is dependent on the frequency, on the Larmor frequency, on the frequency. Wait, come to Larmor frequency later. If you take a number n of those elements and wind them into a loop, then you exactly get that geometry, or that setup as you have it in a birdcage coil. And it is resonant for a certain frequency. And this frequency is, of course, where the phase delays you add up, where they add up to 2 pi. So this structure will resonate and will prepare a certain frequency, and other frequencies will cancel out through those elements. If you now look at the current on one of those filaments, on filament N, you get a cosine dependent dependency. And if you imagine that at a certain time point t, then this omega t will just be an angle offset. And you have exactly the desired, you get to the desired sinusoidally modulated current density distribution. If you switch on the time, then you have the sinusoidally modulated current distribution, and if you turn on the time, then you see that this rotates with Larmor frequency again, or with the resonance frequency, and you have a circular polarized coil which modulates perfectly the desired current distribution on as many points as you put in filaments. So you can arbitrarily approximate the optimum current distribution by putting in more filaments. However, more than 1632 does not make much sense because the gain decreases by putting in more. Okay, now you have an overview on possible coil types and shapes. Which ones are in use? If you come to human use, you mainly have, not totally, but mainly have birdcage coils for volume resonators, and surface coils for areas where you just want to see a certain spot in the subject. More and more, especially in type of surface coils or questions addressing surface coils, phased arrays coils take over. Sometimes even in volume cases. So, for example, if you want to do fMRI, you're mainly interested in the surface of the brain. So array coils with 64 elements and more are not seldom. And even in body imaging, plastering the body with array coils has become quite popular. So you can really mummify the poor patient, if you like, and with moving table even have acquisitions exactly like in CT. Once you apply sequences where you can move the table, then you can do whole body scans and switch through the coils with switching on and off the interesting array coils, surface coils, to completely scan the body. Has large application in metastasis search, of course. Now, probably more interesting to you is if you go from man to mice.
Yeah.
How much time?
You get a few minutes. Yeah. A couple minutes.
Oh, I'll do that. If you go from man to mice, you reduce the volume significantly. So within a plane, you lose a factor of 100 in signal to noise, which is, of course, deadly. As we know, you only measure a small part of the spins at all. So to overcome that, you use higher fields, of course. You go up to 9.4 and more Tesla, and you take coils which fit the sample perfectly. And with that, you are able to receive to get images which are close to the human quality. If we do that, why not do it if the coil is so important, why not do it in a human scanner? This is possible, has some advantages of transferability of the image contrast, but has a lot of drawbacks as you have low T2 contrast and, of course, long scanning times because you got still less SNR as with popular ones. Nevertheless, I'll give you one example. When doing it in a human scanner, you get rid of the standing wave problems, so you can use solenoids and do imaging, in this case of rats. The advantage in human scanners is you can put in more than one animal. This is for two, but they have been built like a revolver and different types where you can scan up to 10 or more mice at once. And you get reasonable image contrast and reasonable images suitable for pure morphology and so. But if you really want to do fancy stuff, you will need an animal scanner. Just an example for coils for animal scanners. Normal surface coils, as I described, birdcage coils for volume. The surface coils have been converted into arrays nowadays, but arrays don't bring that much in animal scanning because the SNR gain is not that big, as the sample noise is not so high. As I have to speed up, I just jump over that. There's a large variety of coils, and you can think of many things. This is one example where the coil is not connected to the receiver by a cable, but by an inductive coupling. You have a second coil up here in a skin chamber experiment, and you just wind a little coil and put it around the skin chamber, and through inductance you can still measure with that, where you have an example here. One thing to point out is if you remember the noise, you had all the losses through the resistance and the temperature in. If you reduce the temperature drastically, you will reduce the noise and therefore enhance the signal-to-noise ratio significantly. There are cryogenically cooled coils on the market already, where the coil itself is cooled down to just a few Kelvin, and this derives an benefit in SNR and of a factor over 2. Just one example here. This is a 9.4 with a less resolution, higher resolution, less resolution, higher field, smaller field. And even the scanning time here is shorter than that, but you clearly see the advantages in cryocoil. You can use them for intravascular, for catheter tracking. You have coils. You can even push them out and do vessel imaging. There's no limits to the different coils. Microcoils, again, I have the same setup and the same geometry. You can use solenoids and windings. You can have array coils as well. These are interestingly enough wound with a wire bonder. And just to give you an idea, you can build your coils yourself. easy coils, no problem, and it is worth it if you do so, because coils are dear. This is just a rough estimate on the prices of RF coils. And finally, to summarize, what is an RF coil? So, in the view of a designer, as I said, it's basically a resonance circuit. In the view of an engineer, it's much more sophisticated, because you've got to do lots of stuff. I just showed you the view of the vendor. The view of the purchasing department is just proportional, anti-proportional to that. The operators often have to work a lot. The patients sometimes don't like it that much. And for you, it hopefully is a resonance circuit now. To conclude, there's a little bit of literature on that. If you want to go deeper inside, you don't have to copy that. I did a few copies and I put them out there. So if you are interested in reading a bit more on the basics, grab one of those copies. And I have to especially point out that one, which is very helpful for a beginner, and where I took some of the graphs as well. Thank you very much.